And what this course is about is the intertwining, the interconnections between your physiology and your behavior, the underlying emotions, thoughts, memories, all of that, and the capacity of each to deeply influence the other under all sorts of circumstances. Now, what we're going to be doing with this is trying to understand this under fairly difficult circumstances. If everybody here was here because they really wanted to understand why all the wildebeest on Earth mate in the same week each year, we'd have a fighting chance of figuring that one out. But that's not what we want to understand. We don't want to understand why birds migrate and don't get lost. We want to understand human behavior. Worse than that, harder than that, human social behavior. It is a huge, messy process trying to make sense of the biology of human social behavior. And just as all sorts of realms, when one deals with messy, complicated problems that you need to think about in some wildly interacting way, we all have a strategy that we come up with. A strategy to make things easier, which is that we think in categories. We think in categories, we take things that are continua and we break them into categories, and we label those categories. And we do that in various settings because it could be extremely useful. What we begin to see here is, in the right areas, we have categories that we impose on things that are not categorical. Here's an example. Why should you do this? Where'd the example go? Here's one of the classic continua that we ever deal with, which is the continua of color, the varying wavelengths that take the rainbow from violet to red, and there's an infinite number of spaces in between. And what do? We have rules in English that you divide the continua here and here or whatever, and that's what you call a color. This is red, everything from here is red, everything here is orange, so on. You take a continua and you break it into boundaries. Why do we do that? Because it makes it easier to store the information away. Instead of remembering the absolute features of something, you simply say, it's a sub-4-minute miler. It's a line that's almost the length, that's about the length of a ruler. It's the color orange. How do you know that's the case? Because go and take people from other language groups where their language arbitrarily divides the rainbow at other points with completely different color terms, and they remember different profiles of colors differently than an English speaker might. Take a color, and if the color comes right in the center of somebody's color categorization, it comes right in the middle of the range of what counts as that color, people remember whether they saw that color or not far better than if you show them a color at the boundary. And people will show that as a function of what language they speak. Taking a continua and you break it into pieces because it's easier to deal with the facts. So we see one of the dangers there, which is when you are paying too much attention to categories, you can't differentiate two facts that fall within the same category. Next example. Remember back at various points of anxiety during exams and such back when, where there was a world of difference between getting a 65 on a test and a 66 on a test. Not particularly different, but because there's this boundary drawn there between passing and failing, there is this dramatic differentiating we make. When you put up boundaries, you have trouble seeing how similar things are on either side of it. What we're going to be having over and over again is any one of these buckets that we spend some time in. All we're going to do is think of that bucket is at that point the most convenient way of describing all of the influences that came beforehand. And in that regard, there's no buckets. All there are temporary platforms, and each platform is simply the easiest, most convenient way of describing the outcome of everything that came beforehand, starting with millennia back in evolution. Okay, so that sounds great. That's what we're going to do. We're going to do this, and we're going to be very sophisticated and fancy in our thinking about it, and we're not going to fall for categorical thinking and all of that. Okay, this is a complicated subject and we're smart, so we're going to try to think about that smartly. That's great, but like maybe this is just an irritating song and dance here of, ooh, we're not going to fall for categorical thinking like people out there. Obviously, when people are thinking about stuff like behavior, and they do this professionally, professional biologists, biology, behavior type, yes, they understand also. This is just this straw man, ooh, we're going to be more sophisticated in our thinking than endocrinologists and geneticists and all of those. They obviously know that these things interact, and there's not just one explanation, and it's just the area they focus on. They understand that. Let me read you a few quotes to show just how much some of these folks don't understand that. First quote, "Give me a child at birth from any background and let me control the total environment in which he is raised, and I will turn him into anything I wish him to be, whether doctor, lawyer, beggar, or thief." This was John Watson, 1912, one of the founding fathers of the school of psychology called behaviorism. Behaviorism that sort of reached its apogee with this guy B.F. Skinner in the 1950s, this notion that if you could control the rewards, the punishments, the positive, the negative reinforcements, you could turn anybody into anything you want, whether doctor, lawyer, beggar, or thief. And we know that isn't the case. We know that's not possible. We know that all you have to do is throw in one other factor, like a lot of protein malnutrition during fetal life, and you're not going to be able to do that. That being a crude example of just how wrong this guy was. You cannot have all the control over the environment and turn somebody into whatever you want. Here's a guy living pathologically in this bucket that behavior could be explained solely by understanding reward and punishment. Okay, next quote. "Normal psychic life depends upon the good functioning of brain synapses." If you don't know what synapses are, don't panic at this point. There are ways brain cells connect with each other. Okay, normal psychic life depends on the good functioning of brain synapses, and mental disorders appear as a result of synaptic derangements. Synaptic adjustments will then modify the corresponding ideas and force them into different channels. Using this approach, we obtain cures and improvements, but no failures. Synaptic adjustments. What do you suppose those little old synaptic adjustments are that this guy is referring to? Any guesses? Somebody shout it out. Electroshock therapy. Electroshock therapy, you know, a little synaptic. You wish it were as gentle as electroshock therapy. This is even more dramatic synaptic adjustments. Any other guesses? Yeah, frontal lobotomies. You know, you want to adjust somebody's synapses, so you just like slice off the front third of their brain or so. Did frontal lobotomies. It had a different name at the time, but was the person who started this, and something that was done to tens and hundreds of thousands of people who had absolutely nothing wrong with them. One of the darkest chapters of where psychiatry gets in bed with ideology, massive criminal destruction of people's brains. This is what he had to say about the procedure on his acceptance of his Nobel Prize in Physiology and Medicine for having invented it. So here we have somebody pathologically living in a world of understand how synapses are working, adjust them, and with that we obtain cures and improvements, but no failures. Final quote, worst one of all. "The selection for social utility must be accomplished by some social institution if mankind is not to be ruined by domestication-induced degeneracy. The racial idea as the basis of our state has already accomplished much in this respect. We may and we must rely on the healthy instincts of the best of our people for the extermination of elements of the population loaded with dregs." Anybody want to guess who that was? Hitler. Nah, Hitler, that behavioral biologist, he was a little bit busy at the time. This was instead one of Hitler's main scientific propagandists. This was somebody living pathologically in a box that doesn't even exist, having notion of race and ethnicity and genetics and all of that, saying, let me fix that one, let me exterminate the elements of the population loaded with dregs, and I'll fix up that little problem of fixing something that ain't broken. Who was this? This was a scientist named Konrad Lorenz. Konrad Lorenz, who probably a lot of us are familiar with. Konrad Lorenz was one of the founding fathers of ethology. We'll learn all about that. But he, like everybody knows him, winding up in all the little kid nature books. Konrad Lorenz discovered imprinting in birds, and he'd be going around. He was this little Austrian guy with this cherubic white beard, and he'd always have these little Austrian shorts and suspenders, and there would be a whole bunch of duckies following him because they thought he was mom, and he was totally charming and irresistible, and this sort of old imprinting with his ducky kids. And he also happened to be a rabid Nazi propagandist who went to his grave saying that there was nothing wrong with what he did. These are not crappy fourth-rate scientists. These are not people working at, the University of the Desert of Podunk or whatever. These are among the most influential scientists of the last century. These are people who influenced how people were educated, and when we decided it wasn't worth the effort of doing it, these are people whose influence led to the brains being destroyed of hundreds of thousands of people who had nothing wrong with them. These are the people who led to the notion that you fix up a problem that doesn't exist by exterminating 9 million people. These are not minor scientists. These are the most influential people of the last century coming out of science in many ways, living pathologically inside their own buckets and how they could explain the entire world. And thus, again, our goal is going to be to not fall for that, to think about human behaviors, and in some cases, to think about some of the most disturbed, some of the most frightening, damaged human behaviors, and resist the temptation to think inside a bucket and find the explanation. Again, every level we're going to talk about genes, hormones, neurons, environmental influence, whatever it is, that point will simply be the easiest way of describing all of the influences that came before. They're not even temporary buckets, there's no buckets. That will be our goal. And this is outrageous because you look at one of these chess grandmasters who's just taken down an opponent and took their queen or whatever, and they will have the exact same physiology as some male baboon on the savannah who's just ripped the stomach open of his worst rival. And we're doing it there just with thought. And some of the time, what's remarkable about us is we have absolutely typical, boring physiology, but we use it in ways that no other animal could. We get stressed by the inevitability of our mortality. We get stressed by reading something awful that has happened to a child on the other side of the planet. We get stressed by somebody zooming past us in some sports car, and we decide that we are now economically inadequate. And you never even see the person's face. You just see the car. We get stressed reading about something awful happening to a character in a novel. This is a whole realm of things that we could do that nobody else does. And on the flip side, we can feel compassion and empathy for a loved one, but we can also do the same for someone on the other side of a planet in a refugee camp. We can feel compassion for a member of another species. We feel badly when our pets are injured. This is another realm where the physiology of the response, the empathy, the emotional bonding, all of that, it's the same boring physiology as every other animal out there, and we are using it in a way that is unrecognizable. Now, some of the time, the challenge is the third category, which is when we are doing something that no other animal out there has anything remotely similar to. What we've got here is a whole novel domain of human behavior, language use, aspects of our sexuality, this profoundly damaging human uniqueness of some individuals confusing aspects of sexuality with aggression. In some cases, we are going to be out there on our own trying to understand what's up. Okay, so that will be the general strategy for the course. We will resist categorical thinking over and over and over, not just because that's cool and nuanced and subtle and all of that, but fall into categorical thinking and you can do unspeakable damage in a realm of science that makes a difference. We will do so thinking constantly about ourselves as a boring species just like all the others out there, as a species that has the same boring physiology but uses it in ways that are unrecognizable, as a species that does some things that are simply without precedent out there, and constantly struggling with what does biology have to do with it. In each of these cases, what's going on a second before, what's going on 10 million years before, where do all these buckets disappear in the interactions? So that's going to be the strategy for the course. Something critical about how the course was designed is it's got no prerequisites, because I really think this is a subject that everybody on Earth should be forced to learn about at gunpoint, and thus, it's a good thing, I think, to have this not be one of those upper-level bio classes. The whole point here is to be able to do this even if you don't have a science background, because the obvious argument I would make is everybody has to learn behavioral biology because we're being behavioral biologists every time we serve on a jury, every time we vote whether or not money should be spent on solving some problem, whether it's a problem and whether it's solvable or not. Every time we try to make sense of a family member sunk in depression, are they having a biochemical disorder or are they just indulging themselves? We are behavioral biologists all the time, so it's a probably good thing that together you will understand the complex thing. And what chaos as an entire field is about, and this was pretty much the first book that was meant for the lay public about it, what chaos shows is that's how you fix clocks. That's not how you fix behaviors. That's not how you understand behaviors. Behavior is not like a clock. Behavior is like a cloud. And you don't understand rainfall by breaking a cloud down into its component pieces and gluing them back together. Has a strength. Each one of those has a vulnerability. They're like, I don't know, Pokemons or something. And you put them all together there, and you get a rock, paper, scissors scenario where you get equilibrium, where they are not attacking each other. Because note, if I am A and I destroy B, B's no longer wiping out C, who's the one who could damage me. It's got to come to an equilibrium state. So you can get the evolution of stalemates like that, and that's quite frequently seen. And note here, this was the evolution of stalemates, not in chimps, not in cetaceans, but in bacteria. What we're going to see is bacterial behavior, to the extent that this is sort of a metaphor for behavior of all sorts of unlikely species are subject to these same rules of passing on copies of your genes. These three different strains of bacteria are competing with each other. None of them are behaving for the good of the species there of the three of them. So rock, paper, scissors is very cool, and you get versions of that in humans, and that's been sort of studied quantitatively, all of that. But that's not real cooperation. That's merely everybody realizing we have to cut back on the competition. We have to cut back on the aggression, because every time I damage whoever, I am more vulnerable in another realm. That's a stalemate. That's a truce. But you look at animals, and in all sorts of realms, it's not just rock, paper, scissors stalemates they're reaching. They actually cooperate with each other. And you look close enough, and you see they're not relatives. They're not relatives, yet you get all sorts of altruistic behavior, and you've got it under a whole bunch of domains. Because this brings up the question, why should you ever be cooperative with another individual if you're a social animal? At every possibility, you should stab them in the back and be selfish. And the reason why that isn't a good idea is there's all sorts of circumstances where many hands make the task light, or whatever that is. Cooperation can have synergistic benefits. And you see that with species that are cooperative hunters, where they are not necessarily relatives. They will chase one, chasing an animal, while the other is getting ready to cut a corner on it. Cooperative behavior, and they increase the likelihood of them getting a kill. Another example of this, research by a guy named Mark Hauser at Harvard looking at rhesus monkeys. And what he showed was he would put these monkeys in a situation where they had access to food. They had access to food under one circumstance where they could reach for it and take it in and share it with another monkey. Under the other circumstance, it required two monkeys to get the food in there. And what he showed was clear-cut reciprocity. Monkeys who were sharing with this guy were more likely to get shared back with and got more cooperation when it was a task where two of them had to work together to get the food. One alone wasn't enough. Many hands make the task lighter. Under all sorts of circumstances, cooperation has a strong evolutionary payoff, even among non-relatives. with a condition, which is you're not putting more into it than you are getting. That is reciprocal. And this opens up the third building block of all of this, which is reciprocal altruism. Cooperation, altruistic behavior among non-relatives, but undergoing very strict sort of constraints of it's got to be reciprocated with all sorts of rules like that. So what does that look like? So you're going to see reciprocal altruism. When would you see that? What's the immediate thing? What sort of species would show systems of reciprocal cooperation among non-relatives? They got to be smart animals. They got to be social. They got to be smart. Why do they have to be smart? Because they have to remember this is the guy who owes me a favor from last Thursday. They need to be able to recognize individuals. They have to be long-lived enough so that there's a chance of interacting with that individual again and establishing this reciprocity. You would thus predict you would see systems of reciprocal altruism only in long-lived social vertebrates. But you see the exact sorts of things in bacteria. You see the exact sort of things in fungi. You see that in all sorts of other realms. You get social bacteria, colonizing bacteria, and where what you might get are two clonal lines that are together. In other words, two lines, each of which is all the bacteria have the same genetic makeup. So think of it as one individual who's just kind of dispersed, another one who's just kind of dispersed, and they've come together in something called a fruiting body, which is how bacteria reproduce or whatever. And there's two parts to a fruiting body. There's one which is the stalk, which attaches to something or other, and then there's the part that actually fruits. So you want to be in the fruiting part because that's the part that actually reproduces, and the stalk is doing all the work there. And what you see is attempts at cheating. Attempts at one of these strains trying to disproportionately wind up in the fruiting part. And what you also see is the next time around, this other strain will not cooperate with it, will not form a social colony. So that's getting played off at the level of single-cell organisms forming big social colonies, getting played at that level. Yes, as we will see, reciprocal altruism works most readily in big, smart, long-lived social beasts, but it can occur in all sorts of systems. So what it's built around is reciprocal cooperation. And intrinsic in that is another motivation going on there, not just to involve a reciprocal relationship with a non-relative and many hands and light tasks and all of that, but also, whenever possible, to cheat, to take advantage of the other individual. And thus, another key facet of it is to be very good at detecting when somebody is cheating against you, to be vigilant about cheating in what would otherwise be a stable reciprocal relationship. And an awful lot of social behavior is built around animals either trying to get away with something or spotting somebody else doing the same. An example of it, there is a test that's used in evolutionary psychology where you're given this very complicated story or another version of a complicated story where somebody promises if you do this, you'll get this reward, but if you do that, you're going to get this punishment, and really complex. And in one outcome, the outcome of it is the person isn't supposed to get rewarded, but the individual decides to reward them. Spontaneous act of kindness. In another circumstance, the individual is supposed to get rewarded, and instead they get punished. A cheater in that case. And amid these convoluted stories, people are much better, 75% to 25%, are much better at detecting when cheating has gone on in the story than when a random act of kindness has gone on. We are more attuned to picking up cheating. And remarkably, some very subtle studies have been done with chimps showing that chimps have the same bias. They are much better at picking up social interactions involving cheating than ones that involve spontaneous altruism. So you see here this balance between cooperation and reciprocal and even among non-relatives, and that's great, but you should cheat when you can get away with it, but you should be vigilant against cheaters. And what of course it comes down to then is tic-tac-toe and giraffe hearts and all of that. What is the optimal strategy in a particular social species for a particular individual? What is the optimal strategy? When do you cooperate? And when do you cheat? When do you defect on the cooperative relationship you've had? And this introduces us to a whole world of mathematics built around what is called game theory. The notion that there are games, formal games, that have mathematically optimal strategies or multiple strategies, multi-equilibrium, and a whole world of research has been built around them in terms of when to cooperate and when to defect. So game theory stuff. This was starting off in a world of like people studying economics and negotiation and diplomacy and all of that, and that was a whole world built around this logic of when do you cooperate, when do you cheat. This is this whole world of Homo economist, the notion of humans as being purely rational decision makers, and what you begin to see in this world of game theory is there is anything but that going on. And later in the course we're going to see something very interesting, people playing prisoner's dilemma games inside a brain scanner, looking at a part of the brain that has a lot to do with pleasure. And what you see is some individuals activate that part of the brain when they've successfully stabbed the other guy in the back. Some individuals activate it when they have both cooperated, and there's a big gender difference as to which circumstance. So you just guess which one is going on there. We're going to see a number of studies like that coming down the line. So the question becomes, how do you optimize prisoner dilemma play? And what emerged at that time was the notion of all sorts of theoretical models and stuff. And then in the 1970s, there was an economist at University of Michigan named Robert Axelrod, who revolutionized the entire field. What he did was he took some Paleolithic computer and programmed in how the prisoner's dilemma would be played, and he could program in as if there were two players, and he could program in what each one's strategy would be. And what he then did was he wrote to all of his buddies and all of his mathematician friends and prize fighters and theologians and serial murderers and Nobel Peace Prize winners, and in each case explained what was up and saying, what strategy would you use in a prisoner's dilemma game? And he gets them all back, and he programs all these different versions, and he runs a round-robin tournament. Every strategy is paired against every other strategy at one point or other, and you look at what the payoff is. You ask, which is the most optimal strategy? And out of it, shockingly to everyone, because this was a computer teaching us optimizing human behavior, out of it came one simple strategy that always outcompeted the others. This is people sitting there, probabilistic ones as to when to cooperate and lunar cycles as to what to do. The one that always won is now called tit for tat. You start off cooperating in the very first round with the individual. You cooperate. If the individual has cooperated with you in that round, you cooperate in the next round. And you cooperate as long as the other individual cooperates. But as soon as there's a round where the individual cheats against you, you cheat against them the next time. If they cheated at you that time also, you cheat against them the next time. If they go back to cooperating, you go back to cooperating the next time. You have this tit-for-tat strategy. In the absence of somebody stabbing you in the back, you will always cooperate. And what they found was run these hundreds of thousands of versions of these round-robin tournaments, and tit-for-tat was the one that was most optimal. To begin to use a word that is not just going to be a metaphor, tit-for-tat always drove the other strategies into extinction. And what you wound up seeing is this optimized strategy. And it was very clear why tit-for-tat worked so well. Number one, it was nice. You start off cooperating. Number two, it retaliates if you do something crummy to it. Number three, it is forgiving if you go back to cooperating. Number four, it's clear-cut in its play. It's not some probabilistic thing. And what you get then with tit-for-tat is, suppose you're playing 3 rounds with another individual, you both cooperate the first one, you both cooperate the next one, you're playing tit-for-tat strategy, so you cooperate on this one, and they stab you in the back, and you can't get back at them because this is the last round. What you'll see is under lots of circumstances, tit-for-tat is disadvantageous, but what the soundbite is about it is tit-for-tat may lose the battles, but it wins all the wars. This pattern of being nice, but being retaliatory, being forgiving, and being clear in the rules drives all the other strategies into extinction. What then emerged was just zillions of people studying all sorts of games like this, and there's other ones. Ultimatum game is a trust game, but it's the same notion of business there, which is you choose to cooperate, you choose to cheat, what's the optimal outcome? There are mathematically optimal outcomes that you can use, and you run all of it against a computer, and you get the optimization popping out the other end. Wonderful. So there's Axelrod and his buddies using terms like, oh, this strategy will drive the other one into extinction. Or this strategy works, but if you program in that every now and then there could be a glitch, there can be a mutation, this will be, they're using all this biology jargon, obviously metaphorically, but right around this point, the biologists look at this, who are just beginning to think about the sociobiology stuff, formal patterns of optimizing behavior, and they say, whoa, does this apply to the behavior of real organisms? Because at this point, it's just economists and computer types and diplomats learning when to optimize, all that sort of thing. Around the time, there was a paper published, somewhat before that. This is a name nobody is going to know, lost in history, a guy named Daniel Ellsberg. Daniel Ellsberg became very famous around 1970 he was working in the Pentagon, and he stole thousands of pages of secret files there and gave it to the New York Times, showing how utterly corrupt everything that went on behind the scenes was in getting us into Vietnam, major blowout, all of that. He had spent the early part of his career perfectly happily working in the Pentagon for the military as a game theorist. Coming up with optimal patterns, and he wrote one paper called The Optimal Benefits of Perceived Madness. What times do you want your opponent to think you are absolutely out of your mind and going to do all sorts of crazy stuff, and where they wind up cooperating to keep you from doing that? The advantages of madness, what's that? That system's where things like mutually assured destruction doesn't work because you're willing to set it off that. The advantages of madness, this whole world of people working on it, mathematicians and war strategists, and there's the zoologists now looking at this saying, whoa, this is cool. I wonder if animals behave that way. And that's when people, now armed with their insights into prisoner's dilemma and tit for tat and all this stuff, started to go and study animals out in the wild and see, were there any examples where this happened? Yes, in all sorts of interesting realms. So people were just blown out of the water at this point, seeing, whoa, forget rational human economic thinking and all of that. You go out into the wild and bats and stickleback fish and gender switching fish and all of that, they're following some of the exact same strategies. Isn't nature amazing? No, nature isn't amazing. It's the exact same logic as saying a giraffe has to have a heart that's strong enough to pump blood to the top of the head of a giraffe, or else there wouldn't be giraffe. And when you look at this realm, it's applying the same notion, the same sort of wind tunnel of selective optimization for behavior in this case, when to cheat, when to cooperate, sculpt something that is as optimized as a giraffe's heart being the right size. So this made perfect sense. Wonderful. But then people began to look a little bit closer and began to see sort of the very distressing real world beginning to creep in there, which were exceptions. And what you suddenly have is the real world. What could be possible explanations? One thing being, maybe they're not really paying attention. Maybe they're not quite that smart. Wait, bacteria are doing versions of tit for tat. What else could be going on? Oh, lions interact in other realms. Maybe this individual is doing very reciprocal stuff, forgiving, overly altruistic stuff in some other realm of behavior. Maybe this lion eats less of the meat and backs off earlier or something like that. Maybe there's another game going on simultaneously. And this introducing the real world in which it is not just two individuals sitting there playing prisoner's dilemma and optimizing. You suddenly begin to get real world complexities coming in there. And by the time we get to the lectures way down the line on aggression and cooperation, what you will see is things get really complicated when you have individuals playing games simultaneously. The rules that you apply to one psychologically begin to dribble into the other one, all sorts of things like that. It will get very complicated. So a first hint there that in fact everything doesn't work perfectly along those lines. Here's another version. Here's one of the truly weird species out there, something called the naked mole rat. If you ever have nothing to do and you've got Google image up there, go like spend the evening looking up close-up pictures of naked mole rats. These are like the weirdest things out there. They're the closest things among the mammals to social insects in terms of how their colonies work. They're totally bizarre, all of that, but they live in these big cooperative colonies that are predominantly underground in Africa, and they were discovered, I think, only in the 1970s or so. And for a while, when zoologists got together, if you were a naked mole rat person, you were just the coolest around, and everybody else would feel intimidated because you were working on the best species out there. And you would see these big cooperative colonies soon shown to not necessarily be relatives, and reciprocity, all those sorts of rules. But people soon began to recognize there would be one or two animals in each colony that weren't doing any work digging out tunnels, bookkeeping. I don't know what naked mole rats do in terms of work, but there would be a few individuals who would just be sitting around, and there was these big old naked mole rats. They were much bigger than the other ones, and they were scarfing up food left and right. There goes Robert Axelrod down the drain. There goes all that optimization, because no one would be punishing these guys. What's the deal? And it took enough watching these animals long enough to see this notion of, oh, there's another game going on in which they play a more important role, and it is sort of dribbling across. When the rainy season comes, these big naked mole rats go up and turn around and they plug the entry to the tunnels there. That's what they do. And suddenly, these guys who have been sitting around doing no work whatsoever all year and eating tons of stuff, they suddenly have to now stick their rear ends out for the coyotes to be around or whatever it is that predates them. What we have is role diversification. Real animals, real organisms are not just playing one formal prisoner's dilemma game against each other at the same time. It's reciprocal altruism. You scratch my back and I'll scratch your back. And whenever possible, you want to instead scratch your back, and they want to make sure you're not scratching your back, or whatever cheating counts as. But trying to cheat, being vigilant against it, formal games where you can optimize it, very complicated. And can you believe it? You go out into the real world and you find examples of precisely that. Optimization with tit for tat. Isn't nature wonderful? It's got to work that way. And then you begin to see how the real world is more complicated, multiple roles, naked mole rats stuck in plumbing, things of that sort. Okay, so these are the principles. And what people of this school of evolutionary thought would say, armed with these sorts of principles, you could now look at all sorts of interesting domains of animal behavior and understand what the behavior is going to be like by using these. Okay, we start with the first example. Here we return to these guys. And we have one species here, and knowing this guy had a penis and this one nursed, we've got an adult male and an adult female. What is it that you can conclude in this species? Males are a lot bigger than females. So let's state it here as there's a big ratio of males to females. Meanwhile, in the next county, you've discovered another species where somebody's got a penis and somebody else is nursing, and their skulls are the exact same size. Oh, here's a species where there's no difference in body size between males and females. Okay, so let's begin to see, just using the principles we've got in hand already, what sort of stuff we can predict. Starting. Okay, which of those species? In one case, you have males being a lot bigger than females. In one case, you've got males being the same size as females. In which of those species, the first one like this, or the same size ones, in which ones would you expect to see more male aggression? First one. Okay, how come? Their bodies are built for it, which begins to tell you something. Their bodies are built for it, maybe because females have been selecting for that. You will see higher levels of aggression in species like this, where there's a big body size difference, and much less of it in these guys. Next, you now ask how much variability is there in male reproductive success. In one of these species, all the males have 1 or 2 kids over their lifetime. In another species, 95% of the reproducing is carried out by 5% of the males. A huge variability skew in male reproductive success. Which species do you get the every male has a couple of kids and that's about it and all equally so? Which one? Second one. How come? Because these guys are being selected for aggression. If they're fighting, there is going to have to be something they're fighting for, differential reproductive access. Okay, so you see more variability in species that look like this. Next, females come into the equation. What do females want? What do females want in the species on the left versus the one on the right? The one on the right, again, skull's the same size, same body size. On the left, what does the female want? What sort of male is the female interested in? Big, exactly. That's exactly the driving force on this. How come? Because she's not going to get anything else out of this guy. This guy is just going to, like the present is going to be some sperm. It might as well be some good sperm, some genetically well-endowed sperm that makes for a big, healthy offspring, increasing the odds of her passing on copies of her genes in the next generation. What about in this species? What's females looking for? Okay. Good. Hold on to that for a second, and let's jump ahead a few lines. One of the species, males have never been known to do the slightest affiliative thing with infants. They just get irritated and harass them and all of that. And the other, you have soccer dads who are doing as much raising of the kids as the females are. In which species do you get lots of male parental behavior? The one on the right. Okay, so lots of male parental behavior here. So somebody just gave the answer here, female choice. What would you see in this species? You want big, muscular guys. You want whatever is selling that season for what counts as a hot male because you want your offspring to have those traits. And somebody else called out here, what do females want in this category? And what was it you said? Good personality, yes. Able to express emotions. That too. Okay, somebody else shouted out something that gets at the broader, more globally Oprah version. Okay, somebody shouted out parental behavior. You want a male who's going to be competent at raising your children. What is it that you want really most deeply? You want to get the male who is the most like a female you can get a hold of. You don't want some big old stupid guy with a lot of muscle and canines who's wasting energy on stuff like that he could be using instead on, reading Goodnight Moon or some such thing. What you want instead is somebody who's as close to a female as you can get to without getting this lactation stuff. Males are chosen who are the same size as females. So the term given here is choosing for paternal behavior, parental behavior, or parental, let's just put that in there. And that begins to explain the top line, species in which there's a lot of sexual dimorphism, morphism, shapes of things, sexual dimorphism, big difference in body size as a function of gender. And in these sorts of species where you get male parental behavior, not much variability in male reproductive success, low levels of aggression, and what females want is a competent male, these are ones where you see low degrees of sexual dimorphism. So how's a female going to figure out that this guy is going to be a competent parent? Once again, we just figured out if he looks kind of like you, because that suggests he hasn't wasted health and metabolism on stupid, pointless muscles when there's more important things in life for making sure your kids have good values. What else would the female want to know when she's first considering mating with the male? Is he a nice guy? Is he sensitive? Does he express his feelings? Is he competent at being a parent? What do you want the individual to do? Prove to you that he can provide for the kids. And suddenly you have a world of male birds courting the females by bringing them worms. bringing them evidence that they are able to successfully forage, they are able to get food. Female choice is built around appearance and behavioral competence at being able to be a successful parent in order to pass on as many copies of genes to the next generation as possible. Okay, how about lifespan? In which species is there a big difference in life expectancy as a function of gender? First one. Here, you're choosing for males to be as close to females as possible, and thus the physiology. Here, you got these guys who are like using huge amounts of energy to build up all this muscle, which takes a lot more work to keep in calories, and you're more vulnerable in famines. You've got these males with high testosterone, which does bad stuff to your circulatory system. You've got males who, thanks to all this aggression, are getting more injuries, more likely in species in which you have a lot of sexual dimorphism in body size, you get a lot of sexual dimorphism in lifespan. And then you look at these guys, and it's basically no difference by gender. Moving on, considering primates that are one of these two patterns, in which one do you always want to give birth to twins? In which one do you never want to give birth to twins? Who gives birth to twins? The one on the right. Of course. How come? Because you got two parents on the scene. You are not a single mother, and you are a single mother rhesus monkey or something, and you give birth to twins, and you do not have the remotest chance of enough energy, enough calories on board to get both of them to survive. A twin that is born in a species like this has the same rate that it occurs in humans, about a 1% rate, and it is almost inevitable that one of them does not survive. Meanwhile, there's a whole world of primate species with this profile where the females always twin. Finally, you are the female, and you are contemplating bailing out on your kids and disappearing because there's some really hot guy over there who you want to mate with, and you are trying to figure out this strategy. So you are going to leave and abandon your kids. In which species do you see that behavior? The one on the right. The one on the right, because you bail out and the male is there taking care of them. You bail out in here and you've lost your investment and copies of your genes for the next generation. You see female cuckoldry, this great Victorian term. You see females cheating on the fathers in this species, but not in species like this, because the father is long gone in 3 other counties there courting somebody else, and doesn't matter, you're not going to get any help from him. In primate species of this profile, you always see twinning. And they both survive. And what studies have shown in these species, and we'll get to them shortly, is after birth, in fact, the males are expending more calories taking care of the offspring than the females. Go bail out on him and go find some other hot guy, which in your species counts as some guy who looks even more like you than he does in terms of what you want out of the individual. So what have we done here? We've just gone through applying these principles in this logical way, and everybody from the very first step was getting the right outcome. And these are exactly the profiles you find in certain species. Among social mammals, these would be referred to as a tournament species. A tournament species, whereas the one on the right is referred to as a pair bonding, a monogamous species. Because in this one, males and females stay together because they both have equivalent investment in taking care of the kids, all of that. What you have here is this contrast between tournament species and pair bonding species. Tournament species, these are all the species where you get males with big, bright plumage. These are peacocks. These are all those bird and fish species where the males are all brightly colored. What are the females choosing for? Peacock feathers does not make for a good peacock mother. Peacock feathers are signs of being healthy enough that you can waste lots of energy on these big, stupid, pointless feathers. That's a sign of health. That's a sign of all I'm getting from this peacock is genes. I might as well go for good ones. That's the world of peacocks. That's the world of chickens with pecking orders, dominating like that, lots of aggression. That's the world of primates where, as in savanna baboons, the male is twice as big as the female. Tournament species, where a lot of passing on of genes is decided by male-male aggression in the context of tournaments, producing massive amounts of variability. in reproductive success, where males are being selected for being good like this, so they sure are being selected for having big bodies, which winds up meaning a shortened lifespan for a bunch of reasons. Females are choosing for that. These are guys who are not using their energy on parental behavior. Thus, you do not want to have twins if you were a female baboon, and you do not want to bail out on the kids because nobody else is going to take care of them. Go and look at a new primate species and see this much of a difference in skull size, and you'd just be able to derive everything else about its social behavior. Meanwhile, these guys on the right, pair bonding species, these are found among South American monkeys, marmosets, tamarins. You put up a picture of them, which I will do if I ever master PowerPoint in some subsequent lecture. You put up a picture of a marmoset pair, and you can't tell who's the male and the female. This is not the world of mandrill baboons with males with big, bright, bizarre coloration on the face and with antlers when the females don't, and that whole world of sexual dimorphism. You can't tell which one is the male and which one is the female marmoset by looking at them. You can't tell by seeing how long they live. You can't tell by how much they're taking care of the kids. You can't tell in terms of their reproductive variability. That's a whole different world of selection. All of the South American tamarins and marmosets, the females always twin. They have a higher rate of cuckoldry, of abandoning the kids. The males take as much care, if not more, of the kids than the female does. Very low levels of aggression, same body size, same lifespan. All the males have low degree of variability. How come? Because if you're some marmoset male, you don't want to get 47 marmoset females pregnant because you are going to have to take care of all the kids. Because as we will see way down the line in lectures on parental behavior, the wiring there as such is bonding with the offspring and taking care of them. No wonder among species like these, you have very low variability. All the males reproduce once or twice. This is the world of 5% of the guys accounting for 95% of the matings. This is totally remarkable because, again, that starting point, you start off here and you look at these and, oh, you can tell if they were bipedal and or are they diseased and malnourished simply by applying these principles of individual selection, reciprocity, all of that. One factoid, you see a new primate species and you see one nursing and one with a penis and they're the same size or there's different in the size and you already know all about their social system. Very consistent across birds, across fish, across primates, of course, all of those, this dichotomy between tournament species and pair bonding species. As we will see way down the line, among some species, types of voles, rodents, that are famous in Hallmark cards for their pair bonding, for their monogamy. So we'll see they're not quite as monogamous as you would think, but nonetheless, a general structure like this. So, one asks expectedly, where do humans fit in on this one? Where do humans fit? And the answer is complicatedly. Are we a tournament species? Are we a pair bonding species? What's up with that? What we will see is we're kind of in between. When you look at the degree of sexual dimorphism, we are not like baboons, but we're sure not like marmosets. We're somewhere in the middle. Variability is somewhere in the middle there. I'm not going near that one. Lifespan, the dimorphism in lifespan tends to be in between, and parental behavior and likelihood of all of those. You look at a number of measures, and by next lecture, we will be looking at some genetics of what monogamous species and tournament species look like, and we're right in the middle. In other words, that explains like 90% of literature because we're not a classic tournament species and we're not a classic pair bonding one. We are terribly confused in the middle there. And everything about anthropology supports that. Is you got to do this, and then this, and then this, and then this. This is an aperiodic system. At any given one of these points, the rules exist for you to know what the next one is going to be. But the rules don't exist for you to know what the 1, 2 down is going to be unless you figure out what this one is. You've got to march through in that sort of way. It's aperiodic. There are no patterns that can be used over and over again. third version is one that's like that people mistake for what I'm talking about here, which is a system which is non-determinist because there's randomness in there. And in that one, going from this one to the next one, there's no rule. It's totally random what the next number is going to be. And the one after that is totally random. And that one, you have no predictability. You're going to have to go every single step down the line, but it's not a determinist system. There's no set of rules that are being applied over and over again. The nature of this one does not specify the nature of that. It's not determinist in that way. That's not what we're going to be interested in here, where randomness comes in. What all of these nonlinear systems are about, these chaotic systems, are ones where they are determinist. There's rules for how you go every step along the way, but the relationship given any given step is nonlinear. They're not identical, and thus the only way to know what's happening 2 down from here is to know what's happening 1 down. The only way to do that, and thus, by definition, this cannot be a system where knowing the starting state allows you to know the mature system without having to go through every single calculation, and knowing the mature state doesn't tell you what the starting state was unless you're willing to do all the back calculations, because it's not reductive in that sense. Where would this begin to sort of manifest itself? Okay, into the chaos book, and I think it was page 27 or so, that you get the water wheel coming up for the first time, and go and look at this picture, obsess over it, understand what that page is about, because it begins to show how these properties of nonlinear aperiodicity wind up producing chaotic systems. Okay, so you've got this water wheel, and it's got these buckets here, and they've got holes in the bottom. And you can have a very simple steady state. You just put in a little bit of water such that the water is basically, as soon as it gets here, it's running out, it's coming out to the same state. This never fills, the water wheel doesn't turn. Now you begin to fill up at a higher rate, and what that does is it's a little bit asymmetrical. This is heavy enough that it now begins to push the wheel down. And as it's going down, this next one is getting filled, and this next one, and all the while it's emptying out. So constant input of water, a rate of things emptying, the wheel turns. It's possible to get a rate at which you're pouring water into the system where it will do precisely that for the rest of time. It will turn at a set speed. It is a steady state, is in the equilibrium state. It is stable such that if you sit here right now and somebody tells you, in this circumstance like this, the wheel is turning this fast in this direction with this force, you can sit there and you can tell them thus exactly what it will be doing 4,070 years from now on Tuesday afternoon. It is a periodic system. You don't have to sit there and go through every second between now and 4,000 years from now. It is steady state, and you can apply a periodic, there's periodicity, there's a reductive quality to it. Now what you do is you put in the water with a little more force. And what begins to happen is the wheel turns faster, because it's filling up with water faster, so it's moving this way faster, and that's great, that's totally logical. But at some point, if you're doing that, there's going to be too little time for these buckets to empty out. They're going to start having more water when they're coming up on this side, because it's moving fast enough that they're not emptying, and at some point, there's going to be enough water left here that it will suddenly change direction. Okay. It's possible, if you get the water pressure just right, that you can get a steady state pattern there. It will go around 3 times when you're putting water with this speed. It will go around 3 times at this speed and with this force, and when it has gone around 3.73 times, it will change direction for 1.7 turns, and then it will go 3.7 times around. And once again, it's a periodicity. It's simply a periodicity with 2 components to it. 2 changes of directions. First time, you're going this way, and oops, this fills up. So you have your first change of direction, and then at some point, the balance is such that you get your second change of direction, and you start the process all over again. There's a pattern, a periodic pattern to it that just happens to have 2 components. You've doubled the number of components in it by putting more force in the system. But once you understand that rule, okay, at this speed, at this rate, with this force of water, it's going to change direction at this point for this length of time, then it's going to change direction again. Knowing that, you can now sit here and be told exactly how full, how fast, with what force, and you could now tell exactly what this water wheel is going to be doing 4,700 years from now. It is still a reductive periodic system. Now you put in the water with even more force. And what you begin to see is, as the wheel is moving fast enough, it will have sort of this first spin in this direction, and then it will change direction. And because the buckets are now emptying out that much slower compared to the rate at which the water is coming in, it will change direction once more, and once more back this way. And you're back to your starting point. In other words, now we have a completely periodic reductive system that has 4 components in it, 4 changes of directions before you get back to exactly the starting point and do it all over again. You've simply gotten a more complex version of a totally predictable periodic system. And what you see is, as you put in more and more water force in there, you keep getting doublings of your periods. You will now get spinning where it goes through 8 changes of directions before it starts the exact thing over again. And doing that, and you can still predict 4,000 years from now, 16, 32, all of that. And throughout, you can be graphing in a sort of a way of representing it. This is the simple system here. That's the single rotation. Here's when you get a first doubling, and it does something like that. Here's when you get the point. You can represent it that way, and you see it is still, you let it keep running like this, and there will be the same periodicity, the same pattern that will go over and over for the rest of time. It's still a reductive periodic system. It's just gotten more complicated. And then, somewhere in the doubling process, something happens. And the something that happens is, it becomes a nonlinear, chaotic system. As you increase the force on the system, the force here being the force of water coming in there, at some point with the force of water increasing, it's going to stop this perfect periodic doubling of the components, and it's going to shift over to a chaotic pattern now. How do you define that as a chaotic pattern? It will shift over to a pattern of spinning this way and then back for a while and going this way. It will generate a pattern which never repeats. There's no periodicity anymore. It generates a pattern that is going to be infinitely different along the way because you're putting that much force in the system. It has become chaotic. And what is obvious here as an implication is knowing here gives you no predictive values ability of what's happening 4,000 years from now. The only way to know what's happening 4,000 years from now is to study what the wheel does for 4,000 years. You can't sit there and recognize a periodicity and just do it over again and again. And what the discovery of chaos was about was that in structured, reductive, linear systems, when you increase the amount of force on it, there's that doubling and quadrupling and all of that. It just gets more complicated and reductive, that there's a transition point where it suddenly becomes chaotic and the pattern never ever repeats and there's no predictability. And sort of the founding generation of chaoticists, this is what they were showing with things like water wheels, where you can see the exact same thing. You have a cylinder, and what you're applying in here, and it's filled with water, and you're applying heat to the system. And what you begin to get after a while is convections, or whatever it's called. Stuff moves, and as you put in the heat it even more, it changes direction. It's the same thing, and at some point when the heat gets high enough, it breaks into boiling, it breaks into turbulence, it breaks into a chaotic system where there's no periodicity, there's no repeating of these patterns. And an amazing insight by one of the first people in the field, this guy York, was that any time you see periodicity of an odd number, you've just guaranteed that you've entered chaotic terrain. that, as he called it, period 3, as soon as you're going, instead of a single period, a double, 4, 8, whatever, as soon as you see the first evidence, as soon as any system like this begins to have 3 components before the pattern repeats, it's about to disappear into chaoticism. So this is what a chaotic system is about, which is you have a starting state, and as you increase the force on the system, the periodicity, the predictability breaks down, and eventually you get, as the critical thing, a pattern which never repeats. And thus, the only way to know what that pattern will be doing X amount of time down the line is to run the system from now until time X. There's no predictability from here as to what's happening at X. You gotta sit there and march through it because it's an aperiodic system rather than one like this. So what the entire sort of starting point for chaoticists was that you get these nonlinear systems, and people have been noting them, mathematicians, physicists, whatever, in systems like that for a long time. And what would they do right around the point that things would become chaotic? They would say, well, this is just getting perturbed by now. It's not functioning properly anymore because it's not working in a linear periodic manner. Something's wrong with the system. Something along the lines of noise and variability. We will stop studying it up to that point. And if you say, we're going to stop studying it until it gets to that point, the last bit of periodicity, what do you come away with? A very distorted view that all the interesting things in the world work in reductive periodic systems. Because what you've just done is say, I'm getting totally disturbed by these nonlinear chaotic things that happen at an extreme, so I'm going to decide they're just anomalies, and we're only going to study in this domain, and reach the conclusion that the entire world works in this domain. Kind of like behavior geneticists who say, ooh, I want to understand the heritability of a trait, and I want to understand it very cleanly, so we're going to study it in only one environment. Because if you study it in a bunch of environments, it gets noisy and variable and messy data. No, it doesn't. It is showing you that the heritability is zilch. It's showing you that you have just artificially excluded your ability to see what's actually happening. And the founding generation, the chaoticists, took the stance that what you've got is all the interesting stuff about complex systems out there are all functioning out in the chaotic realm, and what science has been spending forever doing is looking the other way and pretending it's not there and restricting the studying of complex systems to just these first baby step domains of the periodic doubling. Most of the world is doing this, and most of science has worked very, very hard to ignore this. So once you get this, you begin to get some really interesting implications. So now you find a way, you get one of these chaotic systems, and you first study it when it is still in a nice, straightforward, periodic way. A little bit of water is coming in, and it's turning like this at a set speed, and come back 4,000 years from now, and it'll still be doing the exact thing. It's a great periodic system, and you can come up with a graph of which direction it's turning, would be here or here, and how fast, with what force, whatever, and you will come up with a single dot which represents this rotating in this direction at this set speed, and this is this point of stability, this point of complete predictability. A feature of a periodic system like this, when it's in this boring linear reductive way, is you can mess with it, and after a little bit of time, it will settle back into the same system. You briefly hold the water wheel, and that throws things off, and then you let it go, and it goes back to what it was doing, and it will take a little bit of time for it to go back to where it started. And a way of viewing this graphically is it's doing this forever, and now you go mess with it, you hold it, you turn off the water for a second, whatever, and for a while it does this, and it does this, and does this, and does this, and eventually it gets pulled back to this spot. It goes back to this point of stability, of predictability. It is attracted to this point. And thus linear systems like this have attractors, something where when you mess with it, the system will equilibrate and go back to where it was, attracted to the real solution to the problem. And if you're looking at it at any point here, and it's not here, because it's here instead, and it's here instead, and here instead, all that is noise in the system, and you're in the process of getting rid of the noise back to the pure, perfect state, the pure, perfect description of how the system works. So now you look at what's going on when instead you've got it to the point of chaos, a chaotic system. And what you see is, okay, let's assume that was where the attractor was. And what you see is when you're mapping the speed, the direction that it's turning, the force, all of that, it's doing this. And it will do this for a while, and we'll do this, and it will reach that critical point where suddenly it changes direction, and we'll do this for a while, and then it will change direction again, and then this and this, and what you have is this butterfly wing pattern that became one of the iconic images in early chaos. What do you have here? You've got a description of how the system is working now. Once it's hit this chaoticism, it's not settling down into a repeating pattern. The fact that it is never here and staying there, that's the business that you could never predict. It is constantly oscillating. It is constantly chaotic. So now you ask, and you say, well, that's pretty strange, because it's not actually touching this spot, but it just keeps going around it. It's clearly pulled to it, but in a very different sort of way than when you get a perturbation and quickly it does this. This is being attracted back to this pure starting point. And here, it never actually quite gets there, but it's sort of being pulled by it. What do we have here? We have a strange attractor. And that was the terminology that came into the field. A regular old attractor is one that would pull down to a single stable point. This is the predictable, utterly predictable state of the system right now. A strange attractor is one that has to do with the fact that it's going to oscillate like this, but it's never going to settle down into a single point. And suddenly, there's a very different implication there. Because here, when you're not yet at this spot, what's this spot? It's noise, it's variability, and hang on, and it's going to go away because it will eventually reach the real answer. And systems with strange attractors, what do you make of the variability? It's not noise, it is the phenomenon. There is no absolute pure answer in there. There is not some idealized, the real correct answer, and you're just futzing around here, and if only you had better control in the system, you would eventually get it to look like this. This is a myth. This is imaginary. In complex systems, there is no answer as to what you are supposed to be observing, and everything else is variable noise. This is the system itself. Critical expansion on that. So you're looking at this and you're saying, okay, what is this? This is measuring, in whatever units of time, where the wheel is, what direction, what speed, all of that. It's a whole bunch of data points. And the data points will just keep doing this forever and ever, unpredictably. Wait a second, you say, at some point, it's got to cross that, here, this spot here, and at some point it's circling around and will circle and come through exactly that point. And right now at that point, if you apply the same equations, the same determinist rules, right at that point, the next point should be this. And the next point should be this. And what have you just done? You're beginning to repeat yourself. You've just had periodicity. Wait, this really isn't chaotic. As soon as it hits the same point that was there previously, it suddenly should repeat the pattern all over again. It's periodic. It stopped being a chaotic system. How can this be? Because they've got to touch the same points. Look at all that. And this was the next critical concept in the field, which is you look at this point and maybe its coordinates, 6, 3, and standard graph or whatever. And that's what the coordinate was the first time it was there. And now spinning around, it's just come there a second time. It's back in the same spot. Oh no, it's repeating. It isn't chaotic and unpredictable and going on for infinity. And it just fell apart. It doesn't really work this way until you look a little bit closer. And you look a little bit closer, and it turns out this is not 6 and 3. This coordinate was actually 3.7. And you look closer here, and this one was 3.8. In other words, it's not really in the exact same spot. It never gets to the same exact spot again. Wait a second, well, we really measured it now, and in fact, both of them are 3.7, it's the exact same, and look a little bit closer, an order of magnitude closer, and they'll be, and take it out 1,000,000 decimal places, and they still look like they're in the exact same point, 1,000,000 decimal places out in terms of accuracy, and 1,000,001 is where they will differ a little bit, and thus they're not in the same spot. Critical next concept with this, which is, if that's the case, and they're 1,000,000 decimal places out there, they are differing by 1 decimal place way out there. What that means is the fact that one of them, 4,000 digits out there, is 8.2, and and 3 and a gazillion zeros before that. It means at some point this is going to function differently than this. This will produce a different spot than that. They won't go to the same next place because they're actually different numbers. And if 1,000,000 digits out, that tiny difference will change the functioning of that 1,000,000 minus 1 digits out there. That will then potentially change the functioning of 1,000,000 minus 2 digits out there all the way up. In other words, the consequences of this tiny little difference gets amplified. And this is what's called the butterfly effect. In the standard sort of jargon in the field, the butterfly effect is the fact that the way a butterfly flaps its wings in Korea will change the weather system in Indiana. And this is absolutely the case because of these butterfly effects. The very local consequences of something like a butterfly flapped its wings versus if it hadn't flapped its wings, what have you just done to air movement on the planet? You were 1,000,000 digits out there, and you've just changed that this very last digit went from 3 to 4 because the butterfly flapped its wings, and that's going to cause a difference 1 digit before that and 1 digit, and these are already beginning to differ. And by the time it gets up to any level higher, it's differing enough that the next spot will differ as well. What are you doing? This is why the pattern could never repeat and why it's going to do this instead. Because on some level of magnification in a chaotic system like this, you never have the exact same location, the exact same coordinates occur a second time. Somewhere, however number of digits out there you need to go, the two of them will differ, and that difference can potentially amplify upward in a butterfly effect. If you do it that way, you suddenly have a very different view, which is all the way out a gazillion decimal places out there, and they differ like this. This isn't noise in the system, this isn't variability, this is intrinsic to the system, and the fact that this will now expand, amplify the consequences is why the whole system is unpredictable, because of these butterfly effects. Okay, let me just think about, okay, so critical point here is in this strange attractor realm, not only is there no predictability, that's an important point, and the closer you look, you will still see the same degree of noise, variability. Noise is not something that goes away, but almost philosophically, this critical point in a system, a linear boring system with an attractor, this is the answer. In chaotic systems, there's no real answer, and if you're out here, it doesn't mean that you're not correct. You're not quite there. There is no there. The notion that there is a solution at the center is a fabrication of the data oscillating around there. There is no correct idealized answer in there. This is the idealized answer, which is a completely unpredictable system. Okay. What's intrinsic in this now is this fact that even though you now look an order of magnitude closer, there's still this variability stuff, which can amplify as a butterfly effect up and make a huge difference. And you look an order of magnitude closer, and there's still a butterfly effect potentially, and it doesn't matter how many digits you go down, how closely you look, how good your reductive tools are, the variability is still going to exist down there. And the way to describe this here is, thus, this is a scale-free system. The nature of variability is exactly the same if you're looking at a whole number, or if you're looking at a number taken out to 3 decimal places or 3 Google Flex places, and that sort of thing, that it's independent of how many steps down there you're examining the system. The fact that there will still be the difference, and it can still butterfly its way up to make a difference there, means that all of this stuff is scale-free. It doesn't matter how closely you are looking at it. In other words, the whole reductive philosophy of the closer you look, the better your measurement tools, the more variability is going to go away in a scale-free chaotic system, regardless of what degree of reduction, of what degree of detail you are looking at the system with. The amount of noise is going to proportionally remain the same because it's not noise. It is the system. So you don't have this reductive notion that all we need to do is get better tools and look closer and closer and noise will go away, because it isn't noise. This is the phenomenon at any scale you look at it. And this introduces the notion, thus, of what a fractal is. Because a fractal is a complex pattern, a visual pattern, an equation that produces a pattern, things of that sort, where it is scale-free. The appearance of it is the same no matter what scale you look at. The complexity of it is the same no matter how close you look at it. The degree of variability is the same, because it's not variability, it's intrinsic to the system. Okay, ways to define a fractal, because this has become sort of a very trendy sort of subject, and there's a number of different ways to think about it. Most formally, what a fractal is information that codes for a pattern, where, for example, it can code for a pattern that is a line, and thus is a one-dimensional object, but where the line is moving around with such complexity, with such an infinite amount of complexity, because even if you look closer, it's going to be just as complex proportionally closer and closer. In other words, this is going to be an infinitely long line in a finite space, which begins to make it sound kind of more eventually, this is more beginning to resemble a two-dimensional object. What a fractal is some object, some property that's a fraction of a dimension. If this goes on infinitely, it's a line, but it's really much more than a line, but it's not quite two-dimensional, it's 1.3 dimensions. It's a fractal. A fractal is a system that has fractional dimensions to it, where just the infinite amount of complexity, the closer you look, it's still going to be like this, means that this is a line like no other line. It's one that's infinitely long, packed in a finite space. It's more than a line, but it's not quite a two-dimensional. It's a fraction. It's a fraction of a dimension. That's the formal mathematical definition of a fractal. For our purposes, it's instead, as well, no matter how close or how far away you look at it, the amount of variability is the same. And thus we have absolutely a classic fractal system if these are canals on Mars, or if these are the dendrites of a single neuron, no matter what dimension, without what resolution you were looking at it with, the degree of complexity, the degree of variability remains proportionally constant. It's a fractal. Bifurcating systems are classic fractals, and the variability within the system is constant regardless of what scale you are looking at. And thus, it's telling you the variability isn't noise variability, it's instead what the system is actually about. So I look here. Okay, so you see these fractal properties. The circulatory system is a fractal with roughly the same degree of complexity as is the pulmonary system in its branch points, as in the dendrites of a single neuron, as are the branches of a tree. They're all fractals. Their complexity, their variability is independent of scale. This is what you begin to see in all these physiological systems, these fractals that have equivalent scales of complexity at infinitely different, vastly different scales of magnification. And as a hint of where we're heading on Friday, what that begins to tell you is you can solve this problem of coding for these vastly bifurcating systems where this is made of 1 billion cells and this is a single cell. You can use some very similar rules. And all the rule has to be is scale-free. We will see exactly what I mean by that on Friday, but this begins to solve the problem of there's not enough genes in there. And what this introduces is the notion of there being fractal genes, genes that give instructions that are independent of scale. And we'll see lots more about that on Friday. So you've got these fractal systems all over the place where the point over and over and over again is the variability isn't variability noise, it is what the system is all about. There is no absolute state where the closer you get, the more it suddenly is going to seem clean and non-variable. An example of this in the biological literature, and this was actually a study I did about 15 years ago with probably the most obsessive undergraduate I've met in all my years here at Stanford, which was great because the study was only doable because he was out of his mind obsessive. Okay, here's what the study was about. I was thinking about, well, all this chaos, fractal stuff, amid all of us functioning with the standard model that, God, if only we could measure this down to the single cell level, then we'd really know what's happening because that's going to be so much better than blood values because that's noisy. Working with that model of the more reductive you get, the cleaner the data are going to be. And then here's this whole other world of these nonlinear fractal systems saying it shouldn't work that way. So it struck me to do a study. And what I wanted to do was study the data generated in the scientific literature at different scales of reductionism and see what happens to the variability. And the point here was to make it as well controlled as possible. Thought for some subject that was sort of bio 150 related, and came up with the notion that what would be interesting to look at what are the effects of testosterone on behavior. Just taking any such sort of question out of this course, what are the effects? And you can answer that on the level of societies. Okay? People who are agriculturalists tend to have different testosterone levels than hunters, all of that. How does that affect things like behavior? You can ask that on the level of a single individual. What does a person's testosterone levels tell you about behavior? You can ask on an organ system level. What's happening to blood pressure throughout the body and cerebral oxygen delivery as a function of system, down to a single organ. What's happening to the brain, down to a single cell molecule, all the way down. You see the logic of it. You could come up with something, and do not worry about the details here, something called a coefficient of variation, which is you ask how much variability is there relative to the total size of this. And thus what you will get is, say, a circumstance if this is 100 units high, and in this case this is 10 units high, and in this case this is 50 units high. In this case your coefficient of variation would be 50%. your variance is half the size of the thing you're studying. And in this case, coefficient of variation would only be 10%. It's much less noisy data. So what he did was his little ruler there, and the next 3.5 years with nothing else to do, he went through these hundreds of papers, and for every single figure, he measured what was the mean and what was the error bar in every single figure, and thus what was the coefficient of variation for that error, for that piece of data, for that figure, for that entire paper that would have 11 different bars of data in there. And he's measuring away and going mad from this. And eventually, what he could then do was stick in the average coefficient of variation in all of the papers in the organismal category, and all the papers in the cellular category, and all the way down. Reductive science, what's the prediction? As we go from the big organismal papers all the way down to the subcellular, submolecular ones, the noise, the variability, the coefficient of variation should be decreasing as you get more reductive. That would be the traditional interpretation. The chaotic fractal interpretation would be, it's not noise that you want to get rid of with better tools, it is intrinsic, underneath there, oscillatory stuff, which is the system rather than the discrepancy from the system. It would predict that the relative amount of noise, the variability, the coefficient of variation shouldn't be trending towards decreasing. There shouldn't really be a relationship between what level you were examining the phenomenon and the amount of variability. This was the inevitable outcome of the biophysical properties of a slice of potato. And what he then shows is in plant systems after plant systems, they develop where two shoots come out this way, and a little higher up, two shoots this way, and two this way, and two this way. They're all double saddles, and this winds up being a mathematical solution to a packing problem there when plants are growing their stems. There's no genes specifying it. You don't need genetic instructions. It is an emergent property of the physical constraints of the system. Another example here that's sort of proto-emergence, somewhat simpler versions, this phenomenon of wisdom in the crowd. And this is one was first identified by Francis Galton, who was some relative of Darwin and started eugenics and was bad news in that regard, but famous statistician. And being an Englishman somewhere in the 19th century, he spent huge amounts of time going to state fairs and county fairs or whatever. And he was at this fair one day where they had some oxen up there, and they were having a contest that if you could guess the exact weight of the oxen, you would get to milk it or something. I don't know what the prize would be. And there were hundreds of farmers around filling out little pieces of paper where they were guessing, and what he discovered at the end was that nobody got the answer right. Good. So the owners of this get off easy without having to give up any of their oxen milk. But he then did something interesting. He collected all the little slips of paper, and he averaged all of them, and it came out to the correct weight within an ounce. In other words, no individual in that group had enough knowledge to be able to truly accurately tell what this thing was, but put them together in a crowd, and out comes the right answer. Another version of this, and this one is deeply important in terms of Western intellectual tradition, back to, is that program Who Wants to Marry a Millionaire, does that still exist? In reruns and, okay, so it was this one, they give you questions, and if you answer them, they give you money, and it's great. And at various points, if you're stumped, you got three things you could do. One is they could eliminate, you got four choices, they can eliminate two of them to make it a little bit easier for you. Another is you have this expert who you can call up. And the third option is to ask the audience which they think is the right answer. And all the audience there has these little buttons, so they can choose A, B, C, or D of the multiple choice there. And what the logic is supposed to be is cut it down to two. Your chances are better if you have to guess. Talk to your wise expert who's sitting by on the phone there, and they're going to be wise and be able to hopefully answer this question, or ask a whole bunch of people. And they would all vote, and any smart contestant would choose whatever the audience chose. because when the audience was asked, 91% of the time, they got the right answer. They got the majority of people voting for the right answer, and this is more wisdom of the crowd. And this was a much better hit rate than whoever the expert was on the other side of the phone. One person could be extremely expert, but they're not going to be as expert as a whole bunch of somewhat decent experts thrown together. This is the notion behind a field called prediction markets, where what you do is you are trying to predict some event. For example, the Pentagon is very interested in using prediction markets to try to predict where the next terrorist attack might be. And what you do is you get a whole bunch of experts and you ask each of them to think about whatever the parameters are and take a guess as to how long it will be before the next one occurs. And what you do is you average them up and assume there's a wisdom of the crowd thing going on, and that will give you lots of information. Great case of this a few years ago. There was some submarine or something that sunk somewhere out in the Pacific in the ocean, and nobody knew where it was, but they kind of knew where the last sighting, the last recording was from it, whatever. They had a whole bunch of naval experts, and they had all of them sort of bone up on the knowledge of what was the water temperature and wind speeds and where they were in the last sighting and what was on TV that day or whatever. They got all the information, and each one made a guess as to where it would be on the map, and you put them all together, and they had guesses covering hundreds of square miles of ocean floor, and they put it all together, and they came up within 300 yards of the right location. So what we have over and over here is this business of put a lot of somewhat decent experts together on a problem, and they will be more accurate than almost any one single amazing expert at it, under a few conditions. The collection of these partial experts can't be biased, or if they are, they all have to be biased in a random scattering of directions. And they need to really do be somewhat expert. If you get a whole bunch of people off the subway in New York and ask them to guess the weight of the oxen, they are not going to wisdom of the crowd their way into being able to milk the thing afterwards. You got to have people who have some experience with it. And you wind up seeing wisdom of the crowd stuff going on in all sorts of living systems. For example, here is an ant colony, and here's a dead ant, and they're trying to get the dead ant back to the ant colony. And when you look at these things, they know how to get it, or they get some dead beetle or something to eat, and a whole bunch of ants push it over back to their colony. Oh, does each one of them know exactly where they should be pushing? No, what you have instead is each ant has somewhat of the right idea as to where they should be going, and there's more ants that have a reasonably accurate notion, a smaller number that are somewhat off, a really small number that are way out of whack, because in general, ants are kind of experts at finding ant colonies. They're pretty informed, and what you do is you put them all together and you do this vector geometry stuff, and it moves perfectly in that direction, and no single ant knows exactly where the colony is. You've got a wisdom of the crowd thing here going on. Okay, picking up. So now we are ready to take some of those building blocks, wisdom of the crowd stuff, biophysical potato chips, and begin to see it more formally in this field of emergent complexity. What is that about? What we've already alluded to, it's systems where you have a very small number of rules for how very large numbers of simple participants interact. What's that about? Here's what emergence is about. You take an ant and you put it on a tabletop and you watch what it's doing, and it makes no sense whatsoever. You take 10 ants and do it, and none of them make any sense. You put 100 and they're all scattering around, and somewhere around, I don't know, 1,000 ants or so, they suddenly start making sense. And you put in 10,000 or 100,000 or whatever it is, and suddenly, instead of some little thing wandering around aimlessly, you suddenly have a colony that can grow fungi and regulate the temperature of the colony and all these things. And suddenly, out of these ants emerges an incredibly complex adapted system, an adaptive one. And the critical point there is no single ant knows what the temperature should be in the colony, or if this is time to go out foraging in this direction instead of that direction. It all emerges out of the nature of ant interactions. You've got very simple constituent parts, an ant, much like one box that's filled in a cellular automata. You've got very simple rules for how they interact with each other. Ants have, I don't know, maybe 3.5 rules. Don't tell Deborah Gordon in the department, who's an ant obsessive, but that I may be inadvertently dissing the ants, but they have a small number of rules as to how they interact. If you bump into an ant and you do this with the pheromones, you go this way, and if you go that way, and I'm just making it up, they have a small number of rules, and as long as you got a lot of ants doing this, out of this can emerge hugely complex adaptive patterns. And this is what an emergent system is about. Simple players, huge numbers of them, simple nearest neighbor rules, and you throw them all together and out comes patterning, and there is no single ant that knows what the blueprint is, and there's no blueprint. There is no plan anywhere that says what the mature form of the colony should look like. There are no instructions. It is bottom-up organization rather than top-down. And you see all sorts of versions then of emergent complexity built around, again, lots of elements of things with a small number of very simple rules about how neighbors interact with each other. I don't even need that board. Okay. Here we have 2, 4, 6, 8 different cities, or 8 different places where an ant could find good food, or 8 different something or others, 8 different locales. And you were trying to do something efficient, you need to go to each one of them to sell your product or to see if there's good food there or not. You need to go to all 8 of them, and you want to do it as efficiently as possible. You want to find the way to have the shortest possible path to go to all of these places. And this is the classic traveling salesman problem. And nobody at this point can solve it. There's no formal mathematical solution. And by the time you get to like 8 locales, there's like, I don't know, hundreds of billions of different ways you can do it. So you can't come up with the perfect solution, but you could come up with maybe kind of a good, decent one. There's 2 ways you could do it. First is to have an unbelievably good computer that just by sheer force cranks out a bazillion different outcomes, and in each case measures how much you're doing it, and you can get something close to an optimal answer. The other way of doing it is to have yourself some virtual ants in something that is now called swarm intelligence. Here's what you do. You need to have 2 generations of ants. The first generation, you stick them all down, different numbers of them, and they all start off in these different cities, these different locales, and their rule is each one of them goes to another city. Each one of them goes to another destination. But here's the following rule. The ants are leaving a pheromone trail. Pheromone trail, they stick their rear end down, what is it? Head, thorax, abdomen. They stick their abdomen down, and they've got a gland at the bottom there which releases a pheromone and makes a track, a scent track of the pheromone there. And a very simple rule, they have a finite amount of pheromone in there to expend on the entire path they're making. In other words, the shorter the path, the thicker the pheromone trail is going to be. Now what you do is deal with the fact that the pheromones dissipate after a while. They evaporate, and thus the thicker the path, the longer it's going to be there. You now take a second generation of virtual ants and you throw them in there, and what their rule is, they wander around randomly, and anytime they hit a pheromone trail, they join the trail. one way or the other, and they lay down a pheromone trail of their own with their abdomen. They reinforce the markings on this trail. And let 10,000 virtual ants do that for a couple of 100,000 rounds of generations, and they solve the traveling salesman problem for you, because it winds up being the short paths, the more efficient ways of connecting locales will leave larger, thicker trails, which are more likely to last longer, and thus increase the odds that an ant wandering around randomly will bump into it and reinforce it. And what you see is, initially, there will be every possible path, and as you run this over and over, it will begin to fade out, and out will emerge the more efficient ones. You can optimize the outcome doing it this way, just asking virtual ants to do it for you. And this is exactly how ants do it out in the real world. When they're foraging in different places, there is a first wave of them that comes out, and they go to locales leaving scent trails, and then there's the wanderers that come in, and when they hit a trail, they join it. There are now telecommunications companies that use swarm intelligence to figure out what's the shortest length of cable they need to use to connect up, 8 different states worth of telecommunication towers, whatever they're called, and they can sit there and do math till the end of the universe trying to figure out the cheapest way to wire them up, or they can use swarm intelligence. And that's what a lot of them do at this point. It works. What are the features of it? This is not wisdom of the crowd. This is not that every ant knows a solution to the traveling salesman problem, except none of them have the perfect solution, but put them all together and they all get to vote in outcomes. The ant don't know from traveling salesman problems. The ant knows nothing about trying to optimize this. All the ant knows is one of 2 different rules. If I'm walking from one of these to one of these, the longer I walk, the thinner the pheromone trail. Or rule number 2, if I stumble into one of these, I join it and put down my markings there. 2 simple rules, one very simple type of sort of unit of information, and they're an ant, and all you need to do is make sure there's enough of them, and they solve the problem for you. This winds up explaining another thing. How do bees pick a new nesting site? A bee's nest, a hornet's nest, a bee's nest. Every now and then the bees need to leave and pick a new place to live, and how do they figure out the good place? And there's all sorts of criteria of nutrients, and so all sorts of bees go out there, and what they do is they look for food sources. And they look for a place that will have a lot of food. Maybe that's a place to go and move the colony. So we know already the bee will go out and find its food there, its food source, and will come back in, and here's the colony cut and cross section. And what you wind up having is this ring of bees. Here's the entry, and you have the bee dancing going on that we've heard about in the middle in the dance floor there. And we've already heard it's this pattern of this figure 8 while shaking the rear end, and we know what the information is, which is the angle tells the direction to go out there. And the extent to which it's wiggling its rear end is how long you're supposed to fly for. But the final variable is the better the resource, the longer you do the dance. So you've got bees coming in from all over the place that have found good resources, that have found so-so ones, all of that. And so there's bees doing all this dancing stuff here of different durations. And the ones who have found the good solution to where do we want to live are dancing longer. The ones who have found the most efficient path are leaving a message longer. So now you bring in your second generation, and the rule is, among bees, if they happen to bump into a bee that's doing a dance, the bee responds and goes where it tells you to go. So a bee may randomly sort of bump into one of these guys, and then off it goes. Actually, I'm sure it's more complicated than this, but it's along the lines of there's now random interactions. If one of the peripheral bees bumps into one of these bees that has information, it joins in that bee's group. And it then goes and finds the food resource and comes back with the information. So thus, by definition, if you have found a great food source, you're going to be dancing longer, which increases the odds of other bees randomly bumping into you, which causes them to go and find the same great food source and come back and dance longer, and the ones with lousy ones are coming in and dancing very briefly, and thus there's hardly any odds of somebody bumping into them. And what you begin to do is you suddenly optimize where the hive is supposed to go. Again, it's not wisdom of the crowd, it is an emergent feature of one generation with information based on some very simple rules, and one information that generates some random element, and out comes an ideal solution. More versions of this. Another domain where some very simple rules, out of it emerges something very complex and adaptive. Okay, so the themes here are 2 generations, the more adaptive the signal, the stronger it is, the longer it lasts, and then a randomization element. Another theme that comes through in a lot of emergence, which is to have your elements in there, your ants, your bees, your traveling salesman, whatever the constituents are. And now what the rules are simple rules of attraction and repulsion, which is to say, some of the elements are attracted to each other, and some of the elements are repulsed by each other. Some are pulled together, some are pushed apart, like, for example, magnets. Magnets are polarized in the sense that magnets only have 2 ways of interacting with each other, simple nearest neighbor rules. They're either attracting or repelling depending on the orientation. So here's what you do now. You take a system and something very simple. You've got some simulated sim city sort of thing where you're letting out of a system run to design a city. You want to do your urban planning in your city that you're going to construct there. And what you do is you can sit there and you can study millions of laws about zoning and economics and all of that to decide something very simple. Where are you going to put the commercial districts, and where are the residential districts going to be? Or you can have just a small number of simple rules, which is, for example, if a market appears in some place, what it attracts is a Starbucks. And what it also attracts is a clothing store or some such thing. So a bunch of rules, but then you have repulsion rules, which is if you have a Starbucks, it will repulse any other Starbucks. So the nearest other Starbucks can be this far away. If you have a competitor's market, it can't get any closer than this. That sort of thing, these simple attraction repulsion rules. And what you wind up getting when you run these simulations are commercial districts in a city, where you get clusters of commercial sort of places that are balanced by attraction and repulsion, where you have thoroughfares connecting them, and the more elements there are in the 2 neighborhood commercial centers, the bigger the connection is going to be, the bigger the street is, the more lanes, the more powerful the signal coming through there. And you throw it in, and out pops an urban plan that looks exactly like the sort of ones that the best urban planners come up with. And all you need to do instead is run these simulations with some very simple attraction and repulsion rules. So you do that, and it winds up producing stuff that looks like cities. You do that with a bunch of neurons. You take a petri dish and you throw in a whole bunch of individual neurons, and they have very simple rules. They secrete factors which attract some types of neurons, and they secrete factors which repel other types of neurons. And all of them are having some very simple rules. When I encounter this, I grow projections towards where it's coming from. If I encounter that, I grow projections in the opposite direction. Simple attraction and repulsion. And what you do is, at this point, you throw in a whole bunch of neurons, each one, where you throw them into a petri dish, and at the beginning, they're all scattered evenly all over the place, and you come back 2 days later, and it looks just like this. You have clusters of neurons sending projections, and you have all these empty residential areas in between. And if you just mark this in a schematic way, looking from above, you're not going to be able to tell, is this the commercial districts in a big city, or are these neurons growing in a dish? And you get areas of nuclei of cell bodies and areas of projections, and it winds up looking exactly like that. And amazingly, there was a paper in Science earlier this year, and it was looking at one of these versions again, in this case attraction and repulsion rules with ants colonies setting up foraging paths, and they explicitly compared one colony to the efficiency of the distribution of the train stations in the Tokyo subway system. And what they showed was very similar solutions, but the ants had gotten a more optimal one. And the subway system had people sitting there salaried to figure out the best way to do it. All the ants had were very simple rules of, if it's someone from the other colony, I stay this way. If it's someone from mine, simple attraction and repulsion, and out comes something that looks like this as well. So here you see that happening with a remarkably small number of rules.